Today we're going to make an RC circuit, and we're going to measure the time constant of this circuit. The circuit that we're going to build looks like this. It has one resistor and one capacitor, and it has an input that's coming from P1, which is a PWM input. In other words, it's a digital input. And then the output from this circuit is measured on channel 2. We're going to build this on the Nscope board. So let's get started. I have an Nscope board here. The first thing that the diagram shows is that there is a resistor that's connected to P1 of the Nscope, and that is a 10 kilo ohm resistor in this case. If you build an RC circuit, you might use different resistors and capacitors. But for this circuit, we're going to use a 10 kilo ohm resistor and a 1 microfarad capacitor. So let's do that. We're going to connect a 10 kilo ohm resistor to P1 of the Nscope board. So here I have a 10 kilo ohm resistor, and P1 on the Nscope board is down here. So I'm going to push one end of the resistor into the row that is next to P1. Like that. And then I'm going to push the other end of the resistor just into some other row kind of in the middle of the breadboard down here. And when I push these legs into the board, I want to make sure I push them down far enough where I can feel it kind of hit the bottom of the board. That way I know I've made a good connection between the component and the board. Okay, now let's see what we should do next. Now the diagram shows that there is a connection between the other end of the resistor and a capacitor. So I'm going to take this capacitor. This happens to be a 0.1 microfarad capacitor. So I'm going to look at this capacitor. This says 0.1 on there, so that's a 0.1 microfarad capacitor. And I'm going to put one end of the capacitor into the same row as the resistor. So this leg of the resistor is in the same row as this leg of the capacitor. Now let's see where the other leg of that capacitor goes. Diagram shows that the other leg goes to ground. So I'm going to connect the other leg of this capacitor to ground. I'm just going to push it into one of these holes in the long ground row up there. So now I have attached my capacitor and my resistor in this circuit. The last thing that I need to do is I need to connect the circuit to channel 2. So we can see that channel 2 is connected to this junction between the resistor and the capacitor. In order to make that connection, I'm going to use a jumper wire. So I'm going to connect channel 2 of the Nscope board to this junction between the two resistors. So I push one end of the jumper wire into the row next to channel 2, and then the other end of the jumper wire right there into the junction, into the same row as the end of the resistor and the end of the capacitor. Okay, so the resistor leg, the capacitor leg, and this jumper wire are all in the same row, and then the other end of the jumper wire is over here in channel 2 on the Nscope. Okay? So I've made all of those connections. Now I can go over to the Nscope software and I can actually see what's going on. So here I am in the Nscope software. I'm going to turn on channel 2 so that I can measure the output from the RC circuit, and then I'm going to turn on P1. That'll create an input to the RC circuit. So now we can see that we're getting a square wave coming out of this circuit, but it's kind of hard to tell that the circuit is charging, okay? And the reason for that is because the frequency that I'm using is very slow. And so when I try to look at the circuit charging, I just don't see it. So what I'm going to do is I'm going to do a calculation to figure out what my frequency should be. So let's do that calculation now, and then we can set our frequency, and hopefully we'll be able to see this charging a little bit more clearly. So I have a 10 kilo ohm resistor and a 1 microfarad capacitor. And I want to figure out the RC time constant for this circuit. So the time constant, tau, is just equal to R times C. So in this case, that is 10 kilo ohms times 0.1 microfarads. Another way of saying that is tau is 10,000 ohms times 0.00000001 farads. And if you multiply that out, we find that tau is 1 millisecond. So in this case, with these components, it should take about 1 millisecond for the capacitor to charge up to 63% of its final value. Okay. Now, let's imagine what that would look like. We would have an input voltage that looks something like this, and then the capacitor voltage would charge up something like this, and it would get closer and closer to the final value, but it would never quite get there. Okay, but after one time constant, it would get to 63% of the final value. What we want to do is we want to set the frequency of this square wave here so that we have lots of time for the wave to charge up fully, but we want to be able to still see this happening fairly regularly. So what we're going to do is we want to figure out what the overall frequency of this wave should be. It takes approximately 5 time constants for the capacitor to charge up fully to the final value there. So we want this part of the wave to be about 5 time constants long. This part of the wave is only half of the total period. So the total period has to be about 10 time constants. 1 time constant for this wave is 1 millisecond. 10 time constants would be 10 milliseconds. So the period for the square wave equals 10 times tau. So in this case, that is 10 milliseconds. So that's what our period should be. We want to know the frequency though, and the frequency is 1 over the period. So we say F is 1 over period, so that's 1 over 10 milliseconds. If we translate 10 milliseconds into seconds, that's 1 over 0.01 seconds. So that is 100 hertz. Okay? So what we can do is we can go over to the Nscope software and set our frequency of our square wave to 100 hertz. So let's do that now. So here we are in the Nscope software. I'm going to move this frequency slider to about 100 hertz. Now, it's a little bit touchy and it's kind of hard to get it at exactly 100 if you're just sliding it back and forth. So what you can do is you can right-click on this slider, and then that pops up a little window that lets you type in exactly the frequency that you want. So then you just type in 100 and say OK, and then that sets it to exactly 100 hertz. Okay. So now we can see that there is a lot of action happening on the screen, but we can't really see it very clearly because we're zoomed out so much. So we have to zoom in a little bit. So we can change the time scale here. We're going to bump that up. And now we can see the waves more clearly, but the waves are kind of bouncing around on the screen, moving back and forth. So remember, the way that we make them hold still is we use triggering. So we're going to click on the triggering button here. We're going to turn triggering on. We're going to trigger off of channel 2 because that is the channel that we are connected to. And we're going to move this trigger level up just a little bit so that it catches the wave. All right, so now we can see the wave pretty clearly on our screen, but we don't know where 63% is. We don't have a very clear idea of what 63% of this is. So we want to have a line on that screen that shows us where 63% is. One way to do that is to create another circuit that will make a voltage at 63% of the total voltage. So that's what we're going to do now. In order to create a voltage that is 63% of the total, we're going to use something called a voltage divider circuit. That is just a circuit with 2 or more resistors in a row going between a voltage supply and ground. The way that voltage dividers work is that each resistor gets a percentage of the total voltage, and the percentage that it gets is equal to its percentage of the total resistance. So I've chosen 2 resistor values here so that the bottom resistor is approximately 63% of the total resistance. That means the bottom resistor will get approximately 63% of the total voltage. So if we measure that voltage there on channel 1, that'll be about 63% of the total voltage, and then we'll see that voltage on our screen. So let's build this circuit. The first thing that we're going to do is we're going to connect a resistor between 5 volts and channel 1. So we're going to connect a 15 kilo ohm resistor between 5 volts and channel 1. Here's the 15 kilo ohm resistor. I'm going to push one end of the resistor into 5 volts, and the other end of the resistor is going to go into this row next to channel 1. You might have noticed that the power LEDs for 5 volts and ground just turned off. The reason for that is because I accidentally touched this leg of the resistor to this leg of the capacitor. This leg of the resistor was connected to 5 volts, and this leg of the capacitor is connected to ground. So what I did is I accidentally created a direct path from 5 volts to ground. That tries to use a lot of electricity, and that's more electricity than the board can supply, than the Enscope knows that it can't supply that much, so when it detects that something like that has happened, it automatically shuts itself off to protect itself. And on the screen, it says Enscope detected a power fault. So if you see that, that means that you accidentally touched power to ground and you created a short circuit. If that happens, you have to look at your circuit and fix the problem, and then you can turn the power back on by pushing this button. So you push it once, it goes to sleep, you push it again, and then it turns back on. Okay, so I've now got a resistor connected from 5 volts to channel 1. The next thing that the diagram shows is a resistor connected from channel 1 to ground. That's a 24 kilo ohm resistor. So let's put that in place. So I'm going to take this 24 kilo ohm resistor, I'm going to put one end in channel 1, and then the other end is going to connect to ground. So I'm going to connect it to this long ground row up there. All right, so that should be our circuit. The diagram shows a 15 kilo ohm resistor going from 5 volts to channel 1 and a 24 kilo ohm resistor going from channel 1 to ground, and that's what we have. And that should now show us a solid line at 63% of our voltage on our screen. So when we look over here at the Enscope screen, we can see that we now have a voltage here in red that is at 63% of our total voltage. So we know that it should take the capacitor one time constant to charge up to that red line. So we want to measure this time constant as precisely as possible. So what we have to do is we have to zoom in on this part of the graph where the charging occurs. So what we can do is we can increase the time scale a little bit here. So we've moved that up to 200 microseconds per division now, and we can also move this channel down a little bit. So we can move channel 2 down a little bit so that it's closer here. We can make it so that it starts right about at on this line down here. That'll make it a little bit easier for us to measure things. And when we do that, we want to move channel 1 down as well. So you just click on that and drag it down right on top of channel 2. So they're in the same place. All right. Now we can increase our sensitivity a little bit. So we'll go over here and so if we make that 1 volt per division, or we can make that, if we make it 500 millivolts per division, that just about fits on the screen. So we'll leave it there. And then we'll set channel 2 to the same sensitivity. We'll make that 500 millivolts per division as well. And again, we'll move channel 2 so that it starts in the same place as channel 1. And now we can see we can increase the time scale even a little bit more, or decrease it, so that now we can stretch that out. Basically, we want this wave to take up as much of the screen as possible so that we can use as many of our divisions as possible and make the most precise measurement that we can. Okay? So now we've got this charging stretched across most of our screen, so now we can actually make some measurements here. So remember, what we wanted to find was the time constant for this circuit. We wanted to find, in other words, the amount of time that it takes for the circuit to charge from 0 up to 63% of its total value. So we can do that now by counting these divisions. So we know that each division is 100 microseconds per division. So in other words, each one of these rectangles is 100 microseconds wide. So we can count the number of rectangles, and that will tell us how long it takes for the capacitor to charge. So let's do that. So starting here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9.5 or so. So we have about 9.5 rectangles from when the capacitor starts to charge to when it's 63% charged. So 9.5 rectangles, each one is 100 milliseconds wide, so that's 950 milliseconds altogether. So, I'm sorry, 950 microseconds. Remember, our calculation said that it should be about 1 millisecond, or 1,000 microseconds. So we calculated a time constant of 1,000 microseconds. We measured a time constant of 950 microseconds. So our measurement came out pretty close to our calculation. So that's how we can use the oscilloscope and the function generator to actually measure the time constant of an RC circuit.